Hi, everybody. I hope you all had a great conference. Thanks to Zach for the great introduction. I didn't actually send him an email because he made that all up himself. But Sean Parent started the conference, I think, on the perfect tone by, redoing or going over his first keynote. And this talk is going to be a lot along those lines, even though I baited you with this title into thinking, that I'm going to attack generic programming. Now, I might, but we'll see how things evolve. What I'm really going to talk about is similar to what Sean was talking about, which is the global picture of software development and how complicated it is and how do we get a handle on it. And so to do that, I'm going to take you through some history. Some of it is my personal history and things in my experience. Some of it is more global history. So this all starts in 1967, of course. You all are aware of Edsger Dijkstra, and this particular statement. And this is the quote that I took out of the paper in particular, because I feel like it's quite a statement. I mean, if we could just figure out who is going to work well on our team by counting the go-tos in their code, we would all be done here, right? Like, it would be super easy to hire people and so forth. And it's really a direct attack on the programmers when you think about it, right? Like, he's not talking about some language is the problem. He's saying directly that it's the programmers that are the problem. Now, he basically justifies this as saying that, goto is a license to make a program a complete mess and something that you cannot reason about. And he credits Wirth and Hoare as others that inspired this. He has no data, by the way. There's no science behind this at all. It's just his strong opinion. I'm going to give him the benefit of the doubt on this. I think he was right, whether it was an opinion or whatever. Now, this book is a book that I own. Anybody else have these volumes? See how old I am? That's really the bad news. So actually, in preparation for this talk, I realized I've been in programming for 40 years now. So these books are from the 1960s. These are the collected algorithms of the ACM. It's a fascinating read if you ever get a chance. Here is, out of that book, contemporary with Dijkstra's statement, an algorithm. This is part of an algorithm, a bigger algorithm, a range algorithm, all things, right? You're going to open a book from 1967 and you're going to see a range algorithm with gotos all along the side. Every one of those numbers on the side is the branch goto. Where did this kind of programming come? Well, it came from assembly language, of course. And in this time and period, structured programming wasn't really an ethos. It wasn't a thing that was everywhere. Meanwhile, in the same book, you can read quicksort. Recognize this at all? Again, partition, recursive quicksort. Brilliant, right? Same algorithm we have today. So how did all of this, turn out in the end, right? Well, it's pretty clear that goto basically disappeared from code, right? Does anybody have a coding standard that allows goto in your code?
Yeah.
Oh, okay, we've got a few. But largely it's disappeared from code. I've never seen a coding standard that I've been able to work to that has goto allowed. Certainly in any of the safety and security things, goto is not allowed. Meanwhile, software really became essential to the entire world in the intervening time. And we'll talk a little bit about this, especially in regards to C++, how we got there. And it impacts every part of your life, everyone's life these days. I don't think the impact of software on the world can be understated at this point. The size and complexity of things has exploded dramatically beyond probably wildest expectations. The Linux kernel itself is 25 million lines of code in rough numbers. There's apparently trillions of lines of code in existence. and we're adding somewhere on the order of 93 billion lines of code a year. So we cannot grasp these scale of numbers as humans. Even a single application is not really understandable fully at this point in time. And so this is exactly what Sean was talking about, right? That how do we get a grasp on things this large? How do we actually make successful systems when we've got this kind of scale? So aside from the group that sheepishly raised their hands about goto, actually they didn't. They were actually very bold. There's still unstructured code. It didn't end with Dijkstra because continue and break are basically another form of goto. And these, of course, in C++ and C are used in loop and case statements and switch statements. And, there could be some interesting issues with this, right? Like, you have switch and maybe you have a break or maybe you don't have a break. But those are effectively a more structured form of goto, right? I break out of a switch statement and it goes to the end of the switch. In 1990, this had real consequences. So if you're not an American, AT&T, especially at this time, was the national phone network that comprised the entire country. So at that time, they were using something called a 4ESS. That's a central office switch. That is the thing that your cell phone, your landline phone, nobody here knows. You're all too young to know what those are. That's where you actually connect into the network, which allows you to go anywhere in the globe and actually call somebody else. So these systems are built to be 5 nines. There's a massive amount of testing in these systems. The very first job that I had, I was working for a competitor called GTE at the time, which is now actually merged into Verizon. So I worked on these kind of systems, and I worked in a group that was called the System Performance Analysis Group. And the point of that group was to analyze outages, because at 5 nines you have 2 minutes of outage per year. The amount of rigorous testing and thought and redundancy in these systems was extraordinary. This outage caused somewhere on the order of 50 million calls and 9 hours of constant issue to restore. The root cause was a misunderstanding of break. It's shocking. It's very shocking because the folks that were doing this, knew what they were doing. This foreshadowed something that I think we have today, which is network programming at scale. It's not just about a single computer. It hasn't been for quite some time now. At this time, there's no internet, right? You don't have internets, you don't have cell phones, you don't have networks everywhere. To get a network in a computer, you had to be in special places. So this is the original global network, in fact. And it was built to be very fault tolerant, and still it could not survive. So the 4ESS bug, and by the way, this is heavily edited slide. Mind you, keep in mind the context of the time. The biggest screen you're likely to have at this time can probably display something like 80 wide by 40 deep, because it's a big CRT. Maybe you've got a 21-inch monitor. So the fact that you're already seeing 4 layers of code here down to this if then else should make you worried. And again, this is edited for the slide, and just for understanding. The details of it aren't terribly important, except for this is where the break was added. It was down here in the else clause. And the programmer somehow thought that was going to go to line 13 here. Instead, it fell all the way out of the switch statement. Now, there's obviously a lot of other circumstances surrounding this, right? Like, it's not just this line of code, right? Something had to precipitate this event in the first place. Basically, they had loaded this software. They uploaded this software a month prior to this event happening. And this was supposed to be an optimization, by the way, of this particular processing. And what happened is, in New York, there was a real event with real hardware that triggered an outage. that system tried to recover from that outage, but while it was in that outage, it told the rest of the network, hey, by the way, I'm busy, don't send me anything right now. And the next switch, with the same bug, did the same thing, and the next one, and the next one, and the next one. So basically what we have here is a propagation of an error at a distributed scale that started at a very small scale. And in 1995, one of the observers of this, an analyst, said, here, maybe if we would have had a better programming language, we wouldn't have had this problem. That was 30 years ago, and here we are today. I'm not so sure. Yeah, go ahead.
This almost might sound crazy, but I'm wondering if there was a label at the goto and they said goto here, it would have been more clear where they were going.
You're a good straight man. Just stay there for a minute. So what were the alternative languages at the time that could even do this? By the way, the system I was working on, we used Pascal. It wasn't regular old Pascal, though. It was Pascal with pointers and a lot of other things around it. So, it wasn't like at this period of time you could just drop in any language and make happen what they were making happen. So by the way, Python, just as curiosity, resisted having a switch statement for a very long time. And what they call break is called something else. I can't even remember now. It's not called break. You can't be confused. So, good straight man. Break to label. That might have cleared it up.
Isn't that just a goto?
It's just a goto. It's the same exact thing. So, this is in C23. Yeah. And it's a proposal for C++29. Do we want this feature?
Yes.
Python rejected this feature on the basis that the abuse of it would be stronger than use cases for it. I don't know. But here's the thing. What are we talking about here? We're talking about reasoning about programs, right? What kind of programming language construct is good for us? What kind of programming language construct is bad for us? Anybody know who this is?
Grace Hopper?
Margaret Hamilton.
Margaret Hamilton. That is the Apollo flight code. So this is that 1960s era. And by the way, when I started my career, this kind of thing was not unusual at all. A whole ton of printouts would show up in the office because the monitors weren't very big. So it was much better to read code this way, believe it or not. Do you think a single person can even understand that? No. It takes a team. So Dijkstra's point, I believe, was that as soon as you start scaling things at least a little bit, readability really matters. There's something about being able to reason about that code because in the end, the machine only does what we tell it to do. It doesn't make its own stuff up, except for now it does because we have AI. And it makes stuff up. But the basic problem here is we've got local reasoning that failed and we have distributed consequences. And we have this in spades today. So when I think about the mental model that we have, we basically have a programmer on the left. They've got some idea. They write some text. A compiler puts it into the computer as binary that executes, right? That's basically, at a 10,000 foot view, that's what's actually happening. So the readability, of course, isn't for the machine because the compiler takes care of that part of it for us. It's for the other programmers. And so in the end, when we start thinking about, I'm solving a problem, I've got an algorithm in my head, how do I know that it's been transmitted to the machine in a correct way? And I'm going to argue that we don't know. And that is the source of a lot of the issues that we face today. Okay, let me roll you a little bit ahead to 1977. This is the Voyager spacecraft. There were two of them, Voyager 1 and Voyager 2. And by the way, these pictures that I'm showing you here are photos that were taken of the outer solar system by Voyager. It's an extraordinary thing, actually. There are 2 spacecraft that have now been operating for 45 years. They have 3 onboard computers. They're 18 bits. So you can tell JF that not everything has 8 bits. Oh my God. 18-bit onboard computers. They have a grand total of 69 kilobytes of memory. It's astounding, right? 69K. It's insane. The software is written in assembly language. And there's a lot of table-driven logic, which makes a lot of sense to me because when I started my career, I was writing assembly language in 8086. And table dispatch and table constructs were a very common feature of assembly language programming. So because of the nature of what Voyager is, when you think about it, it's an extraordinary achievement because it comes at a time when, again, there's no actual network, but you have a command and control facility that's in California that has to talk to an antenna on the ground somewhere halfway across the world, and then it has to talk to a spacecraft in space, right? So you have to write networking code. You have to be able to deal with the fact that, hey, by the way, this is a multiprocessor capable thing on board. Why are there multiple processors? Because the processors of the day, could not, in fact, do the mission that was needed with the science mission and just even the radio communication back. It has that feature.
Wow.
Right? This is ubiquitous now. I can remotely patch the phone, everything, right? Like, this is going on constantly now. It was there for the whole time. You just didn't know that one team over here had actually invented all this stuff. So that stuff really matters, as it turns out, because in 2023, Voyager 1 started sending garbled data down its data links. And so the communication from the spacecraft was unintelligible, basically. No one knew what was going on. And just to give you the context, it's 15 billion miles plus away from Earth at this point. And so, to send a single command to it and get a response requires 44 hours. So you can go about your 2 days, and before the response is going to come back. So, of course, they were able to fix this problem. In April 2024, you'll notice there was a decent gap of time there. But basically what they realized is that one of the memory banks had a problem. They were able to deduce this from various patterns in the data and their understanding of the hardware and the spacecraft itself. And operations were fully restored after a software upload, which basically worked around the data bank. They can't go fix it. Nobody can go fix it. It's too far away from Earth, right? The entire software team and hardware team that made this was all retired. So they had enough information, they had enough history and so forth that they could do this. I consider this a remarkable achievement of engineering. Excuse me. So what have we learned? Well, for one thing, we've learned that hardware matters, and we shouldn't ignore it. Physics matters. When you start to deal with things that are very far away, maybe even not so far away, right? Like even just geosync orbit, physics matters in communications. And communications is a big part of this. But understanding the machine and the software and the mapping was essential to being able to repair this thing remotely. It's also true that complexity, even at this time, was real and there. All right, now I want to fast forward. I want to fast forward to part 2, which I call abstract harder. So I showed you the mental model of somebody that's writing code. It's some text, and that's going into the machine, and it's being translated into binary. So in 1998, I was just finishing up my first stint in the space business when I was working on a project called Iridium for Motorola. And there was just a massive number of things going on at this time. Number one, C++ standard 1.0 was appearing. We had been using C++ since the mid-90s at that point. And of course, everything at that time was object-oriented. It was just completely object-oriented design. That was the only one true way, essentially. Design patterns and software reuse and all of these things were going on. Code generators, DSLs, frameworks like Corba, where you're generating massive amounts of code so you can do networking. Because, networking is now becoming a real thing that a lot of people are having to do. So in my work, I was trying to grapple with all this because that system was about a 5 million line of code system developed by about 300 to 400 engineers. And, I was tasked at some point in trying to figure out how the interfaces are going to work in this distributed system. Fortunately, I had been doing that actually since the beginning of my career. But at this point in time, a few things started to happen. And I'll explain a little bit more about the UML side versus the generic side of the programming. So why UML? So, of course, UML, everybody knows what that is, right? It's the winner of the Booch Rumba, or they came together, however it worked, didn't really matter. So people are talking about this as seriously, this is the blueprints of software, this is how we can see things. How about generic code? It's horrible. It's just awful for generic code. Like dealing with the idea of a function over here and a data structure over here, UML is not made for it. It's made for O. However, even as I say that, there are real things in UML that are real and substantial. When I went to engineering school, because I didn't get a computer science degree first, I got a systems engineering degree, we were taught state machines. And why were we taught state machines? Because state machines allow you to model interaction and so forth. So just like Sean was talking about a domain-specific language, you can think about this as a way of thinking about a problem. You can use this with very abstract models. Or you can make it executable. Steve gave a talk about coroutines and how they embody basically what is a state machine. So there's limits to it, right? Like it's not necessarily going to help you understand a huge code base. Having said that, when I was working in telephony, in fact, we had a state machine compiler. And actually all of the features associated with your phone were drawn up as state machines, and they were run through a compiler, and it was executed by a Pascal engine that knew how to execute state machines. I feel like this is sort of a lost art. When I talk to young engineers, nobody knows how to make one of these. They don't understand how they work. It takes practice. Like, you don't just see how to draw this diagram and figure out what it means, how to deal with guards, callbacks, all this stuff. By the way, of course, there are state machine libraries and all kinds of things in Boost and all over the place. People do use this, but I feel like it's sort of an underutilized thing. So again, how do we get a handle on a bigger program? If I can make it like this and make it clear to you, and then it's just automatically a set of code, I don't have to actually worry about grinding out code every single time. So that's one track. Dependency management is another thing. Code dependencies matter in big systems. I need to be able to split code up in some logical way, right? I need to be able to separate the concerns of code so I don't have a big ball of mud, which is all just intertwined with each other, right? And so one of the things that I've done over the years is look at the dependencies and components and then take something from the networking field and basically think about the idea of layers of abstraction and dependencies. And when you look at this, you can organize a large system typically into things that are very non-specific. So in other words, if I'm doing mathematics, basic algorithms, right? Those things apply to lots of domains, right? Many, many domains. If you're doing finance stuff, like there's specific things about finance that don't break down into that particular thing. And actually, when you start to think about generic design just for a minute, you realize that the dependencies between things is really the key to what generic design is about. We're going to separate the algorithms from the data structures. So this is a diagram from the book that I wrote. And I don't believe most of what's in that book, by the way, at this point in time, because I've learned a lot since then. But I still believe in this part where things like foundational things like basic data structures and algorithms belong in the bottom of this. They don't have any dependencies to anything else. Things that are at the higher level, your application, which you've composed together from the lower level things, does. So this is a technique you can go read about and understand. But at this particular time, right, there is just an explosion of C++ publications, okay? You'll notice that maybe some of the most famous publications are not here. You know, Scott Meyer's publications are not in this list. But if you're thinking about, you know, the design and so forth and evolution of C++, to me, these are the things that I look at. And so, of course, it's really funny. I think I have, later on, I'll show you the reaction to generic programming in the STL that was at the time. It was astounding because generic programming is fighting an uphill battle at this point. Because again, everything is object-oriented. But Copeland, who's an object-oriented guy, also recognized that, wait, maybe there's a little bit more here, right? Like from a design perspective, there's other things we can do. And then there's generative programming. And due respect to my colleague over here, he's written a book too, which didn't quite make the list. But generative programming in Sarnecki and Eisenecker is metaprogramming is one way to do it. There are other ways that they cite. And of course, elements of programming came later. I think its timing might have been somewhat unfortunate. Okay, so this is the definition that Sean showed the other day. And I got his permission to steal it from him. Because I really like this definition, and it's really great. You've all seen it once before. I'm not going to dwell on it right now. But here's the headwind. One of the best class libraries in existence at the time. What do you notice? Okay. Object root, bit set, collection, linked list. I mean, it's nonsense. Right? I mean, this is bad. Like the dependencies are all wrong. The thinking for this is all wrong. The separation of concerns is all wrong as compared to what went into the STL. On the other hand, there's this. I'm going to use the word ergonomics in the rest of this talk to talk about, you know, what the programmer's vision of this thing is, right? This is a pretty tame example of a generic program from 1998. This one is pretty tame because, you know, the iterators are pretty short and so forth. You know, you've got your algorithm over here and so forth. So it's pretty tame. It's not too verbose, but it is verbose. It's more verbose than is actually necessary as we now know today. Yes?
Did you forget the second iterator in the erase?
Oh, no, I didn't forget the second iterator in the erase. It's also bug prone because there needs to be a second iterator here. It doesn't do what you think. This code only deletes the first two because it's calling the wrong thing. So this is an example of what I'm talking about. The programmer has an idea for what they're doing. This all looks very reasonable, you know, to everyone except Stephen. But because he knows what this bug is, right? Like this bug was a problem for a very long time. People, you know, didn't grok it. It compiles. It runs, but it doesn't do what you expect it to do. So there's a number of ergonomic things here, and we will come back to this, and we'll look at what's happened in the intervening time. So, generic datetime library. So, on that same project, I came to the realization that OO was a false prophet, as it were. And how did I come to that particular conclusion? I came to that conclusion because on a 5 million line of code project, we had 3 datetime libraries. 3. And it's like, why do we have 3 datetime libraries? And that's because none of the datetime libraries that were in existence at the time, including our own, factored the problem correctly. They didn't think about how it was going to do. And by the way, you know this library is boost datetime. And boost datetime was predicated around the idea of fundamental value types. Dave and I had discussion on this very stage when I was winging it before you came in, Dave. Zach was reliving the first BoostCon. But the topic that was with Kevin Henney, who couldn't make it, was value types and what they meant. And at this time, I don't even know how I figured it out, but maybe probably reading Kevlin's things and so forth. But, you know, this seemed like a very principled approach to things, right? Like I've got a series of types. They give me a way to express what I need to express in a very good way. This, of course, is the forerunner to standard chrono. Many, you know, thanks to Howard Hinnett for really making standard chrono happen in various forms. And I'll say a little bit more about that again. So how was this library different, right? Like how was it generic? Well, for one thing, separated the math algorithms that have to do with time out of the actual fundamental types. They weren't built into some object-oriented structure. They're templatized, of course. The idea of a clock was separated from the actual types that it produces, right? Because the clock is a fundamental abstraction on hardware, not on the representation of the time itself. One of the problems in that 5 million line of code program was I have to be able to replace representations because, by the way, the length of time that I need to represent needs a 64-bit integer or a 32-bit integer. 64-bit machines were not common at the time. And you wanted to be able to deal with this idea of resolution, right? Like, so milliseconds or seconds and converting between those things in some first-class way that doesn't break your program. It also had a replaceable error policy. By default, it was exceptions. Boost datetime is all exceptions. No one ever used the replaceable policy. Replaceable calendars. That was a nice theory. No one ever did it. So, was boost datetime a failure or a success? Well, you know, it was a success. Many people used it for a long time. You shouldn't use it now. There are better options. But code understanding, like the library code, you know, it's not completely ununderstandable, but it's not easy to understand. The user code's pretty good. But a coherent package of these types, like if you wanted to make it, you know, a 128-bit underlying type, requires 10 plus types. And that was a problem I couldn't really crack, right? Like you just got to write all that stuff and you got to know how to write it and it's weird, okay? The facilities we have now are much better. Keep in mind, we're dealing with GCC 295 and, you know, MSVC, whatever, that doesn't even have the ability to have a template member function properly. I mean, it'll compile, but then it'll fail at runtime. Here's another thing. I/O. I/O is a pain. It's a real pain. It doesn't abstract away easily. And you have these mini DSL things, right? Like this, that you use for I/O. And they don't port to anything. If I have a Mayan calendar system, this doesn't mean anything. And things like the time zone database and the data storage and all that stuff are a big pain. All right. How about standard chrono? Failure or success? I'll poll the room. What do you guys think? Good?
Success.
Good.
Success.
Okay. Good. All right. Because what you were going to get instead of that, which I believe I can hand to anybody, even a non-programmer, they'll basically get what this is, right? What you were going to get was C. You were going to get time val, which is a horror. And I've probably said that here on this stage previously. time val is a horror, and the C programmer should be embarrassed about time val. Not only is it hard to use, but it wastes bits, and that's a horror show. So bottom line is, I think it was an absolute win. This stuff for threading was much more understandable. Now, this is the point where I depart from the story, because at that point in time, after the absolute horror it was to get this approved in the committee, I quit the committee. I didn't like it there. It was not a nice place to be. For a decade, I quit, basically, until Marshall Clow, who is another longtime member here, convinced me to come back to the committee. The committee changed a lot in that time. But the bottom line is that actually the chrono that you have is a much simplified design. And I don't think that was a bad thing for us to simplify the design. The other design, with all the genericity, would have been harder to use. Now, there were other compromises that were made that I actually still don't agree with today. Okay? And if you want to know about those, you can talk to me later. So, I did skip over one thing. The timing of this, boost date time, library, and so forth, was basically coincident with Andre's modern C++ design. And I had been working on this before I read that book, and after I read that book, of course, it made all the difference in the world. What's interesting about that book, when you think about it deeply, right, is that, he advocates for policy-based design, and you take the smart pointer and you break it all into its essence, right? And you get 120-something variants of the smart pointer. So imagine testing that, right? Like 128 variations of the smart pointer. So this leads you to think sometimes more generic isn't better. By the way, that stuff never showed up in the standard, right? We never got, something that's 120 versions of smart pointer. Okay, let's go ahead to 2010 and beyond. So, yes.
I just wanted to point out that the whole policy-based thing, if I look back, it looks to me like a total failure, and it was not part of Alex Stepanov's
very good observation. Agreed.
Right.
And of course, but so that goes back to the question of, well, Andre takes generic design and calls it one thing, and it, so. But I totally agree with what you're saying, Dave. So, and even what I was doing might not be, in some respects, considered generic design. I think the separation of the algorithm part from the data structure part, for sure. The rest of it, maybe some other things. But, it's still instructive to understand. So what happened in 2010? Well, the train model appears, right, in the standardization committee, and things accelerate rapidly, right? Things are now on a regular cadence. In 2018, Boost Asio becomes the inspiration for the networking TS. I was the review manager for Boost Asio, by the way. It's a brilliant piece of design. By 2020, Boost is barely a part of standardization. It happened rapidly. Ranges, the most important library probably in there, and format, probably the second most important library in 2020, go around. Many other libraries go around. So the context of the world actually changes out from underneath us. There are significant headwinds for generic programming, in my opinion. Concepts gets rejected. John knows this very well. And it doesn't get back into the standard for another 9 years. In the meantime, metaprogramming, another compile time technique, flourishes. It expands. Programmers get really smart. They realize exactly what they can do with this tool. And despite what Sean said on Monday, it helps generic programming because it deals with being able to look at overload resolution and so forth. But there are other factors, right? Const expr, lambdas, these other things come into the language and they change things. So we have a new version of the programming model. we've got some idea, then we've got some sort of generative code that's going on in there. And then finally the stuff gets to the compiler and the computer in the instant pot. What? Sorry, the AI generated it. Obviously it's correct, right? It took like 7 prompts to get there. And I'm just like, I don't get it. Anyway, I thought it was funny. I laughed out loud when it produced this because there was no pot in the prompt, nothing, right? But the point here is that there's this step now that's in front of the final set of code, if you will, that is codified by the compiler into binary. What else happens? Concurrent programming is off the hook. Almost every core comes with multiple cores. Programmers are faced to deal with the fact that they're not going to get a 20% bump every year, from CPU, and it raises the bar again, right? Like, how hard is it to reason about a concurrent program? Super hard. I try to avoid it as much as I can. Distributed network systems. By 2010, I don't know about everyone, but how many people have a machine that doesn't have a network today? You do? Wow.
Little embedded processors.
Oh, so, well, I mean, you're saying a little embedded processor, but in fact, websites run on embedded processors all the time now, right? Like, you're running a network stack and a website on everything.
I'm building a Metal 2 clones.
So there's another next level of difficulty in reasoning about programs and trying to understand. And, the question is, are we going to be helped here? The documentation is a real problem. From yesterday, here is CPP reference for the TS for networking. Anybody know what these red things mean over here?
There's no page.
There's no documentation. 0. Okay, so you're forced to go back to ASIO to get documentation for this. The ASIO documentation in and of itself is problematic. Yeah.
Surely it's in the standard, right?
This is not in the standard, it's in a TS.
Oh, it's okay.
But
well,
still,
it's documented in the TS, surely.
Mm-hmm.
Something is written in the TS, but I guarantee you, Dave, that it's not a user's guide. I mean, and this is a real problem, right? Like, if you're a programmer and you want to know how to write a network program, there's no guidance here. There's nothing. You're on your own. Now, listen, Michael Case and other people came to this conference and explained how to use ASIO. So there's like talks online that you can go see and so on and so forth. But this is really not sufficient, in my opinion. This is what you got elsewhere. That's Python. 2 lines. Boom. You could copy and paste it out of something in Stack Overflow, right? In 2 minutes, and you would be going. Okay? Complexity kills. If you can't understand how to write the program, you can't write it. All right. What's my time? Do you know what time is? 45 minutes? Okay, good. We're doing well. All right. Part 4. Apologies to Metallica for the second one. So, what do we know about the machine? These are all things we know, right? Virtual functions are expensive. Bounds checking is expensive. Generic programs bloat your code up. Exceptions are expensive. Who believes these things in this room? You, 2, 3. Very good. See, now you're starting to think critically, and that's exactly what this talk is about. Thinking critically about what it is in relative to what and how. How was it measured? How did we decide that virtual functions were expensive? Around about 2012, some Google engineers put this chart together. This is actually still 2012 numbers, so don't rely on it for the current world. It's probably changed. This is about physics. This is physics of a machine, a modern processor, right? and modern compute systems. L1 cache access, half a nanosecond. Everything else is the factor of that, right? So we can see branch mispredictions in here, more memory. Main memory is 200 times slower. Has real consequences for programs, right? Over here, weirdly, we have this thing compress 1K bytes using Zippy, which has become snappy, which is something that actually is runs in parallel. This is mostly just talking about standard execution of things. Here, sending us something over a network, as you can see, starts to get relatively expensive. And I say relatively because the second page, it's all off the charts, right? Like disk I/O, anything that has to do with anything, a long way away gets super expensive. I didn't put the factors here. I was too lazy to calculate it. Again, this probably no longer applies because if you look at the, SSD numbers over there, they're all changed. Now, this is going to be where it starts to get controversial because I know a number of people in this room are going to say that they absolutely know how their machine works. Oh, well, there's that guy. David Tangled. But actually, what David's talk was really about here is to refresh all of us on, right? There's actually an underlying machine here, and it might actually matter what that machine does. And since I started programming 8086 assembly, I should know what this machine is. I have no idea what this machine is. I don't program in assembly anymore. I'm abstracted 4 layers away from the machine at this point, right? But the point is that, okay, now we have an understanding of like registers and basic things like that, right? But in point of fact, that doesn't tell you what you actually need to know to understand it. So it's also the case that assembly, because really Matt Godbolt did us all a favor by creating Compiler Explorer so we could actually then go see the assembly that was going to go into the machine in a trivial fashion. But the problem is we got all of these other things going on, right? And none of that is expressed in the assembly in any way, shape, or form. You can't see whether the processor is going to speculatively execute 6-way parallel, rearrange your instructions. You don't know. I highly recommend Linus's talk from yesterday. Thank you, Linus. Because he goes into, a single instance of a single processor and breaks all this down to some level of degree. But here's the problem. That's one study on one processor in one environment. It can't go very far. If you go to an ARM processor or some embedded processor or somewhere else, you have no idea whether it's going to behave the same. It might not even have half of these features. So how do we reason about the performance of anything without understanding the machine? Yeah.
There are some tools you can use.
Understood. And by the way, your talk is also cited here in a minute. So don't get me wrong. There are people who know things about how the machine works. But what I'm saying is in the big picture, it's very hard for you to know about all the aspects. So far, we are only talking about regular old serial execution with nothing special. And performance measurement lies because what? What machine, what cache? What I just said. How fast is the cache? How big is the cache? What compiler, what options? There's so many variables here that I challenge you to show me one study that even takes one algorithm and shows it to me on 20 machines and how it performs. I've never seen one. It's entirely possible I've missed it. Yes.
I would argue that because the hardware becomes so heterogeneous and because our ability to reason about it is decreasing so rapidly, that the compiler's optimizer is supposed to fill that gap. That's the entry that says we write one thing and it gets translated to the correct place.
Yes. Dave.
I think I think what I do, if I think about how I operate, is I have an abstraction that accounts for these things in a sort of a general way. And I'm not generally writing code that I'm trying to tune for one specific processor.
Right.
But I do know there are cache effects, and so like I lean on locality, for example.
Yes.
And I understand the principles of branch prediction. And so I try to take those things into account when they matter.
Absolutely. And I think there's no question that many people in this community are doing something very similar to that. But that misses the point in the end. So, performance analysis means, what am I talking about here? I'm talking about counting instructions. We've known forever that instructions are not created equal. That is not a thing. Back when I was programming in 8086, that was actually pretty true. Right? It was, one cycle per instruction and so on and so forth. But we expect when we see an algorithm say, oh, I'm going to have n comparisons, or I'm going to have n log n, or I'm going to have, n squared, that there is an association to the performance, whether that is true or not. Okay? And what I'm trying to say is, I don't think it's as true as you might think, because of exactly what Dave was talking about. Things like memory access matter way more, perhaps, than the number of instructions you're doing. And the existence of things like flat map is a clear indicator that we're willing to sacrifice what, in theory, would be a more optimal data structure by performance analysis because of memory.
Well, I mean, Big O doesn't tell you how fast a thing is.
That's right.
It tells you how it scales.
Right.
And, often constant factors overwhelm that, but at some point, that usually bears up the scaling factor.
Well, I think the evidence is starting to accumulate that it's very difficult, and hold that thought for a minute because it gets deeper. So let's talk about virtual functions again. Let's go back there. Where did the slowness discussion start? Well, back in that 2000 era book on page 215, Sarney describes virtual dispatch and the costs, virtual table construction, all of this kind of stuff. Difficult to predict. Yeah. My esteemed colleague in the front here has a talk in 2023. It might be pointless. My own personal measurements on an arbitrary machine that you don't care about, because what would it matter what machine I did it on, indicate that virtual function dispatch on a relatively small virtual table is in the 2 nanosecond range. Okay? So it's so far in the noise that it doesn't matter. Now, why am I even talking about this? Why do I even have a design in this era, right? Like everything is static and generic and whatever. You know what? I had a design that needed dynamic dispatch, and if I would have reinvented it myself, I think I would have done it much worse than C++ just does it out of the box. My point is, don't assume that this trope and many of the other ones are true. I'm going to skip over this because I did not finish the slides. Okay. And here's where we finally get to the death knell of the thing, is because parallel execution just absolutely destroys serial execution. And it was one thing when it was just a small thing here or there, but it's now everywhere. Google told us that hashing was a problem and that data structures were a problem when they invented their highway library and they went and made a hash map that used the capability of having SIMD underneath. Compression is absolutely, every single compression algorithm now uses SIMD. Regular expression parsing. Right. So our regex library is completely destroyed, basically out of the box, by stuff that can run in parallel. Basic algorithms like lower bound can run dramatically faster. We're talking factors of 10 15. These aren't small factors. And it starts to cut when you think something like SIMD-JSON, because SIMD-JSON isn't like the obvious application, the obviously parallel application that comes to your mind. But in fact, it's there and it's real. We use it internally. It's fast. It's way fast. Way faster than any best handcrafted linear code that you can come up with. It has limitations. The algorithms underneath it are absolutely dramatically different than what you would write for serial code. Oops. Sorry, pointer is going too fast for me. So, see the two talks? Ruslan has a talk. Dennis has a talk, both at this conference. And they walk you through, what does a parallel algorithm look like? How does it actually work? It's radically different than a serial algorithm. And when you can get this, it's extremely fast. So here's the problem with parallel algorithms. You've got to rethink them. They're different. They work differently. It's a different machine. It's a different context. And that's my point. At the end, if you're paying attention to this machine, you can program it to do things in a dramatically faster way. APIs end up changing. Google's point was, I can't have the hash map have a bucket list because the internal data structure has to change, right? If I expose the bucket list from my hash map, I'm dead. I can't parallelize it. Ruslan's paper is worth studying just for understanding, how parallel range algorithms are going to work in C++26.
Hopefully.
So all I'm saying is the ground is shifted yet again underneath what we think are the performant, efficient algorithms. Where it finally hit for me was Daniel Lemare posting a blog on date parsing, because it's something I know about very keenly. One of the biggest requests I ever had with Boost Datetime was, why is the date parsing so slow? Why is the timestamp parsing so slow? Well, it's because you're using this stuff. You're using this SERF stuff. And I got to have basically an input range, and I'm using, C out and C in and all that kind of stuff. I got to cache stuff to really understand how to do this. Well, here's the C version of the algorithm. It's so horrible. I get ill looking at it, honestly. Just all of the things that you could just do wrong here, right? And this is what you would have got if you didn't get Chrono, by the way. So you would have had something like that. Here's what that algorithm looks like in Intel Intrinsics, plus or minus. You two guys know what it is. The rest of us will just look at it. What does it do? It's actually, so many less instructions, and it dunks 8 times faster. Now, this isn't an obviously parallel thing, right? This is a small data set. It's not like some long data set where you obviously get all the benefits of, pulling in from the processor a long stream of memory, with very fast caching and so forth. This is 15 bytes, and it destroys it. Your mileage may vary, right? But I'm pretty sure I'm not going to be able to outrun this on processors that have, decent instruction sets. All right, 30 minutes, good. We're in good shape. Part 5. Where are we at? Whoops. The clicker is just doing it to me. All right, here's the definition again. So clearly in C++, generic programming is one. There isn't any debate about it, right? There are no OO-based collections or any of that kind of stuff. OO is almost dead to this entire community. Have we realized the dream? There is less code. When you write good generic code, you have less code. It's amazing when you take good types, regular types that are well defined and put them in, they just work. You can customize things in ways that are just beautiful, really. Some of these abstractions are extremely efficient, right? On Monday, and I'm afraid I didn't cite the presenter.
I think it was me, Jeff.
Yes, okay. Sorry, and what's your name again?
Steve.
Steve. Yeah, so Steve's talk, he's showing range views outperforming standard STL code. Why is that? Largely it's because of lack of copy, right? Like you've got this view, it's lazy, you can do this pipeline. The core STL abstractions really have not changed, right? I mean, when we think back on, what the data structures look like, there's been coloring at the edges, we've added some functionality to various containers, and we've definitely added algorithms, we've added parallel algorithms. So we've definitely made some interesting progress here. Let's go back to the ergonomics of this thing, which is buggy, right? Any guesses how many lines of code it takes now? That's it. There's a lot of change here, right? First thing, they didn't have to say what type is on the vector, right? That doesn't really have anything to do with generic programming. It's just a language feature that helps you write it more cleanly. We have a reshaped here. Could be troubled waters ahead. And then we have this print thing. And what's interesting about print for me is you wouldn't think about it as generic necessarily, but really it is because we've got an arbitrary number of parameters here, and we can specify how they're going to be formatted in this single line of code. Oh, wait, it's a range. It's not just a single value anymore, right? We're just doing that with a range. So the range thinking and that evolution of the library has dramatically changed the ergonomics. Let's go back to the reshaped and the definition. Completely independent of the underlying data representation. I have bad news. This is a container algorithm. It is not a generic algorithm. There is an overload for a reshaped for every container. Even though it's a free function, these are container-based. So every single container that we add to the standard library, we have to add that. And why did we do that? It's a concession to ergonomics. The other thing that we had back here is buggy and hard to use. This is trivial to use. I'm not sure. How many people know about these algorithms? Half the room? That's scary.
Jeff,
Yes.
surprisingly, I am from parallel algorithms world, but I didn't know about this algorithm. That really surprises me.
Okay. Yeah. So I'm going to also say again, we have a documentation problem. This is not new. I'm not going to say exactly who, but a rather important person in our community wrote a book and didn't include these algorithms. It's a concession to the data structure, in part. I would argue this is nothing new. Right? What's wrong with this? I mean, this is beginner 101 C++, right?
It won't compile.
Doesn't compile.
It won't compile. Why won't it compile? Because list does not meet the constraints for the sort algorithm, which requires a random access range, right?
And it shouldn't.
And it shouldn't.
There's no reason you need anything more than forward sugar.
Right. So what did we do? We said, listen, you can sort your list, but you have to do it this way. It's a breakdown, a concession to the data structure. It's a concession to the machine and the way it works is my feeling about it. Let's talk about other ergonomics related to generic programming. Yeah.
If I'm not wrong, in EOB, Alexander talks about linked iterators, and then the sort would be the linked, so the same sort that we have on a map.
I'm sorry, I'm not following the question.
So the reason why list has a method sort is because you need an operation that is not supported on list iterator. It's a relinking thing.
Yeah.
So in EUP, if I'm not mistaken, they talk about linked iterators, and then if you had linked iterators, then the standard sort could do this.
It really depends on what properties you expect the standard sort to have, like address stability of elements. For example, if you relink, then you know
Yes.
you've changed the result with respect to the address of the values.
Yes.
So but what's missing? I've been holding on to this, and I don't know whether to say it now or later. But I took a walk with Alex not long ago, and Alex is retired and doesn't like to talk about programming, but every once in a while he'll say something. And he said to me, I view my generic programming project as a failure, and it's probably not for the reasons you think. His vision was that the STL, everything he established is an example.
Yes.
And as far as I can tell, Alex's project, by and large, has stopped. Right? The project was there's another step in a description of what generic programming is that you didn't cite, which is raise algorithms and data structures to their highest level of abstraction without loss of efficiency.
Yes.
Right? And so if we're recognizing that SIMD doesn't match the abstractions we have, there's a whole project of searching for the abstractions that let us do that stuff.
You are a great straight man, Dave. Thank you. Hold that thought. I'm getting there. Yes, absolutely. So the point is that what Dave was saying, right? Like, so the data structure and the abstractions and what our expectations are. There's no question in my mind. We could make this sort work against the list. We just make it call the member. So like mechanically we can do it, but we won't do it because we're saying these are the properties that standard sort has to have. All right. Everybody knows these. Increased compile times, complicated overload sets, complicated specifications. Well, you might not know that one, but if you sit where I sit, you know this one. And difficult to test. And, I'm going to keep harping on this one because the documentation is truly bad. All right, this is 2025 full generic algorithm. What's the algorithm? Anybody got it yet?
I know what the algorithm.
All right, I cheated on you. I reversed the name of the algorithm so it'd be harder to see through all of the constraints that you're looking at, right? Like, sorry, what was the algorithm? No, you're not fair.
Merge.
What's merge? Okay, we got it. Yeah. Okay. This is strict right out of Ruslan's paper. That's why he's the doppelganger. So, what have I even got here? Right? Yeah.
You even miss one parameter, which is an execution polygon.
No,
the top one. Just scroll down a little bit if you can.
Oh, you're right. I'm sorry. Yeah, it doesn't actually fit on the slide because there's
the
more.
Interesting thing is there. Yes.
There's more, right? This is a simple algorithm. Merge is a simple algorithm. It's not hard to understand at all. But, if I give this to somebody that has never seen this kind of thing, they're just like, what are you even talking about here? Like, right?
Even if you give it to someone who has seen it.
Yeah. That is exactly right. This is what I look at and the other people in LWG look at on a regular basis. This is the kind of thing. And so now I'm supposed to try and extrapolate as a user what I could write that would satisfy whatever list of constraints there are here. By the way, do you need a constraint solver to kind of like propagate all of them? It's really hard. This is not a good thing. Yeah.
Yeah, just for all of you to understand, this is the simplified version of the signature after LWG review. More complicated.
Right. We figured out a way to make it a little easier to read. Let's take another example. Standard expected. This is the simplest thing in the world, right? It's just an error type. It's no problem. Here's a couple of things that, an error type, a regular type. What could go wrong, right? This looks fine, right? It is fine. Now it's not fine.
What does this have to do with generic programming?
What's that?
What is the connection of this example to generic programming?
Well, people think this is generic programming, whether it is or not. And here's the thing. This is not okay. This will compile and it will fail. Right here. You would be able to access this, and it's because this thing has a constructor. So here's the problem. You see it? Sure. Steven? Come on.
I haven't even read through the whole thing.
Okay, I'll show you what the problem is.
Oh,
Yeah.
The problem is there's a missing constraint. So you have to prevent the construction from unexpect. And again, from a user's point of view, this looks all fine, right? Like it doesn't seem like it's a problem. Now, this was passed over by all of us in LWG, myself included. Completely missed it. Had no idea. How did we find out about it? There was a bug report. That bug report comes, 3.5 years after this paper was reviewed and put in the standard and all that kind of stuff. There are dozens of these kinds of things.
Sounds like it was unexpected.
Well played. More imperfect ergonomics. C++23 code. Any idea what happens here? I have two things, right? Like I've got a new range algorithm for contains, and I've got a member function on string for contains. Right. This free algorithm, of course, is, disconnected from the class. That's the way we do generic programming. Well, as it turns out, it doesn't work. Like this doesn't actually compile. And that's because this char thing isn't it isn't a range. It isn't the right kind of range. So then we have another thing called contains subrange, actually. So that's how you actually have to write it. So we had to write the name differently. Here's the problem. It doesn't behave like you expect. I know, David, you're shaking your head. This is exactly why we're having this talk.
Is it because foo is an iterator? Becomes a char star that is an iterator?
To be honest with you, I don't know why this doesn't work. I just, I was making this example, right? Because I wanted to demonstrate, here we can have, a generic algorithm of the same name and the same behavior as an algorithm on the type itself, and it should produce the same result, right? No. And that's because of the way we've specified it. Yeah.
Would it work if it were a string view?
Yeah, it would.
Yes.
Yes.
It might.
Yes.
But the point is, these are, the holes that regular programmers can run into. I'm not a regular programmer. I ran into it because it didn't occur to me that, that would work. So testability, explosion of test cases, complicated specifications, complex cases. So what's my verdict on generic programming? It's a tool. It's a capability. All tools have benefits and limitations. And in this talk, I've mostly focused on the bad. Okay, and it's an easy thing to do, and I really don't want to do it because the good side of it is amazing, right? But realize it's a tool. It's not the be-all, end-all of everything. Just like object-oriented design was not the be-all, end-all. Yeah, Dave.
Yeah. So I think one thing that a lot of people don't realize is that the project of doing generic programming the way Alex intended it is a huge investment.
It is.
It is not something you can do casually.
Correct.
And the payoffs are amazing, you know, when you figure it out.
Mm-hmm.
But it takes a lot of contemplation. You know, a lot of what at least what I have done in my career as a programmer is drink some coffee and focus on the code and do this, right?
Yep.
And generate some code and make a thing do something.
Yes.
Right. And as I've matured as an engineer and a programmer, I've realized that's not where the ultimate value lies. That's how you get sprawling code bases that don't work.
I don't know about you, Dave. I want to go in the forest and walk. That's where the ideas come. Okay. Where do we go? Echoes of 1967 and 1990. So, about multi-paradigm design, in 1998, this was what was said. It's true, C++ has a number of pitfalls. Here we are. We're 2025, and we still have a number of pitfalls. We really need to get rid of the pitfalls. We're at a crossroads. It's very clear. Other languages are deciding to honor something more important, like safety. In the standard, we have a start. We have runtime safety with contracts and the hard and standard library. It's a start. It's not nearly enough. We're going to get more generative programming. That is for sure going to happen. We have structured concurrency. As much as you might not like it, it's there. We have SIMD, and we have constexpr with everything. I haven't really talked about constexpr and its effects, but the reality is a lot of things can actually be tested by the compiler now. There's been many talks on this subject. And virtually everything in the standard library, short of a few things, will be constexpr now. So much, much more code will actually be testable at compile time. And I think that's an important point. The generative part of the static reflection, I think, just means that it adds that whole other dimension to library building. We need to make a more solid foundation. At this bottom layer, we can't have the problems that we have. We've got to get rid of what Richard Paul reminded me of is the C problem. We just need to stop writing C in C++. Except for, it would be one thing if I could just instruct you to go use the standard to just write C++ code, but I can't because we have bad numeric conversions. We have other things, lots of unsafe APIs, resource management issues. So here, it's C++, right? What's wrong? Yeah. It's undefined behavior because, of course, this is not initialized. It's amazing how many C programmers I've shown this slide to. And once I explained to them what the lambda was, they still didn't get what the problem was.
I think you said
Sorry, what's the other reason?
Multiple
It was slideware and I messed it up. Fine. So, Howard Hannett and another individual are working on something called better integer numbers. Like if you're programming Rust, right? Like you have better number system. You don't have overflow, the stuff that was shown on the first keynote, right? So better behave integers is one version. Boost safe numerics, having big integer types, these kinds of things that are math, right? Like math is in every application in the world. We need to get better with floating point. We need to solve the hard problems here because floating point is a disaster everywhere around. There's a lot of different ways. We have a decimal float. There's been some discussion about whether that's the right direction. I don't know for sure. I'm not that smart about it. Fixed floating point types, possibly. There's a thing called posits, which is very much a floating point-like capability with a much better thing. It gets rid of nans and that kind of stuff, right? So having something that, well, the main thing about posits is it honors math, right? You expect that if you add A plus B, parens plus C, that's exactly the same as A plus parent B plus C, right? That's standard mathematics. Floating point does not honor it. Posits do. Being able to actually compare two values, floating point values, and actually compare them is one of the things that posits says. Okay. From chars to chars is a disaster. It's C in C++. Yet, why do we have it there? In part, we have it there because there are newer, better, faster algorithms. And for some reason, I wasn't there for it. We decided that, that was the API. But we don't even use our own stuff, right? Like, we don't even use optional or expected or any of these things because, of course, timing, right? Like, this stuff showed up before we had those things. Now we have those things. We have better ways to actually express these things. So from my point of view, and this is hardly a new idea, right? This has been talked about. But now I believe we sit at a precipice where we really have to reconsider the standard library 1.0, Dave, thank you. And we have to look at the fresh world as it is with all the tools that we have available to us. And that includes contracts. We can do this. It's not hard. Put it in a different namespace. However we want to do it. Don't break the 25, 50-year compatibility, whatever. We can do it. We need to replace hash, right? We need to have a hash that works with the best things. If you're writing code in C++ today and you want a hash table, you will not use std hash or any of them. Yeah, Brett.
Would it be okay if we just had regex2 and hash2? Would you want to have all names too?
That'd be fine by me. I think there's a lot, this is just not a difficult problem to solve, in my opinion. Yeah.
Well, I mean, one of the problems is the core language needs the same treatment.
There is that.
So
I agree. I don't disagree with.
Invest in this.
And as you know, there are various directions down that line. And I'm focused on library here because, in part, this conference started as, and in my opinion continues to be, about library development. And I think there's a lot we can do. We can make very solid progress. So, I'm going to call Sankel out again because, he's very strongly about, how do we, just abandon C++. He's not really saying that, I don't think. But what I would say is we got millions, probably billions of lines of code. This stuff isn't going anywhere. And we need to give a path to the people that are going to continue to use C++ to a better world. And we may not be, I hear people say, theoretically, we can't make this language safe. We can't deal with these problems. I believe actually, practically, we can deal with many of these problems and we can make the place better and we can make it performant and we can adopt new algorithms and so forth. Another interesting example, right? We have core guidelines that say, you should have the ability to say this pointer is not null. Don't we have to rebuild smart pointers to be able to do that properly? Because that's basically what GSL does, right? So maybe we should put those in the standard, right? If we're going to talk about some of those kind of subjects. Let's do collections 2.0, right? Let's get rid of the stuff we don't need. Let's make parallel enabled versions of whatever. But maps and vector, those are the two obvious ones. Does anybody use std list? No. Why? Because, okay, maybe there are a few. But listen, std list isn't used because, in part, it's faster to use a vector, even though it's demonstrably worse from a code analysis point of view or an algorithm analysis point of view. Hannah has a very interesting talk from Meeting C++ on hashed array mapped trie, which is basically a form of hash map that is vectorizable. And it has interesting properties, like you can have stable iterators into it as you do things. maybe we just need to shed iterators. Dave.
Just on the subject of linked list, it actually is a useful data structure for some things, especially
Yes.
in compilers when you're generating code. But my colleague on the Hilo project has, Hilo doesn't have any reference semantics in it, so there are no pointers to linked lists, right?
Right.
But we built a compiler in Swift with value semantics. So how did we do that? Well, you can make a thing with the properties of a linked list except for memory address stability. But there's another stable identifier you can use that where it's all in a vector and it's faster.
Yeah.
And she's just written a paper where she demonstrates you really don't need these references at all.
Yeah.
Right?
I mean, listen, you can write a very large amount of modern C++ without ever using a pointer. But we have to teach people how to do it. Now, there was actually just a talk that came up on Reddit the other day. Klaus Engelberger, if I'm saying his name right, has written modern books about C++. He demonstrates how to do it. And we need a lot more of that, because otherwise you're going to see the stuff from the AI, which is based on crap that somebody wrote 10 years ago.
Here's a thought about rewriting the standard library, because even when we write these parallel vectors, all these improvements that we're talking about, at some point something will go wrong, and then we'll have to write standard library 3 and then 4, and then what
Yes.
does that end?
Yes, that's what software amounts to, right?
Instead
It can't
of
be.
fixing this current standard library is, I think, what a better solution.
It can't be in stasis unless it's 15 billion miles away. Oh wait, even that's not in stasis, because you can upload changes to it.
I think that in imagination, yes, you can imagine C++ kind of addressing some of these issues and things along these lines. But I don't think the community is capable as a body to come up with a decent standard library 2.0. The things that are happening with standard library 1.0, I see it actually getting worse. I could see a freeze on the standard library resulting in better results than the absolute absurd amount of complexity that's being added.
I mean, you are obviously not alone in your view, right?
Right.
You can see that view on social media.
But the thing, and sure, social media agrees with me, but being in the committee, I don't know how to fix that, right? In library evolution working group, I'm frequently one of only a few voices that says, this is way too complex. There's no way we can move this forward. Users will not use it. And, back when I joined the committee, that was the dominant voice, I felt. At this point in time, it's drowned out by all the hundreds of people that came in and don't have that historical perspective or haven't been trained in that stuff.
Yeah.
I don't know. I would love to hear how that could be solved, because
I don't know how to solve it either. If I had solutions for everything, I probably wouldn't give this talk. Part of the reason I give the talk is because you all are smart, and somebody might come up with the right idea. Inbal, and then Dave, and then you.
Respond as. So, a few things I want to say. First of all, the things that you've seen on the slide, they all have either implementation that I can refer to and that you could basically take as is, or papers. And I really do see a future in that. So I don't want to go into the discussion of ABI breaks to 2.0 or whatever, but we can have them either in better names or replaced or whatever. But I don't see any actual reasoning that we can. And second, I'm sympathetic to your view, David. I am not sure I experienced this the same way. I do admit that some of the new things that we got are complex, but on the other hand, you have seen some of them during this conference, like reflection and standard receivers, and I think they do have a lot of value. So at the end, the question is, who are we targeting, and what kind of, who are the developers that we're targeting? And I feel, looking at the standard library, that we have utilities that target both newcomers or people that are less experienced when they want to do something simple, like what Jeff showed in 3 lines. But we also have things that are more complicated, because we do want to have this
Right. So
That's how I feel.
So I'm
Yeah.
going to let Dave
Anyway.
speak in a second, but I do want to respond to that a little bit. This affects every programmer, every single one. I don't care if you're the most advanced generic programmer. It affects your programs because you can write correct ones, and you can't now.
And Jeff's simple 3-line programs that were using constructs designed for beginners were wrong. Many of them. Not always because Jeff made a mistake, because he was showing that the complexity of our standard library.
But he was using with a C string. I just want to say, and if we're trying to.
That's true.
I'm not saying.
Inbal, you have to know not to do that. That's the problem.
Yeah, that's the problem.
That's the problem.
Okay. I'm not claiming.
So a string literal is a C string.
All right. I just want. I'm not protecting. Okay.
So
let me just.
Let me just say with Dave here. So in my model, right, like the compiler, right, that thing that's in the language, that's the language point you're making, right? Like it can lift it.
Yeah.
That's a problem of our imagination for how does the compiler work and what does it do with that literal.
Agreed.
So yeah, sorry, Dave, go ahead.
All that aside,
yeah.
So this is a grand call for a large rethink, right, of how we approach things. Now, in the committee, getting such a grand rethink accepted depends on some agreement on principles of what's important. And the reason that I stopped working with the committee was I discovered that any agreement on principle fails. And people since me have experienced the same thing. Google tried very hard to achieve some agreement on principle, and that failed too. Okay, so from my point of view, I completely agree with David, and I will come out and say it. I think C++ is in a long tail of decline now, and absolutely the existing C++ code needs to be maintained. But when I think about what's going to make programmers powerful in the future, it's another reason that I went on to do Swift and left C++, because the thing that's going to make programming better overall is not investing in this.
Okay. Can I quickly?
Okay.
Did you
So hold on. We got Steve.
Wait. But I have a response. We have policies.
No.
Dave, did you hear about policies?
Okay.
I just want to say, I asked about hash 2 and vector 2. You said I don't know what to do. David says he's skeptical that we can get work done on ISO. But you both agree that would be great. I'm sure that'd be great to see a beam in hash 2.
Yeah, I don't think this is a technical problem at all.
So,
it's a people problem, like Dave is pointing out, right? Like,
so a lot of these problems can be solved by being productive about doing good library design,
right?
By people using these things in real code.
Yes.
And real usage of real code and real production.
Yes.
Is a very good argument for a standardization of that stuff.
Right.
So I think we should all agree that there are steps we can take to move forward.
Right. As long as there's this.
Fine, but everyone else can have a vector that it doesn't have all the sharp edges and things, right?
As long as there's those proposals, I see no reason that we wouldn't get them. They're not yet there yet, but some of them are. And I just want to quickly address Dave. So I don't know if you heard about policies. This is a project that I've been doing in the past year or so since I started. This is an agreement that is trying to be a committee-wide agreement on how do we write libraries. And this is trying to achieve exactly what you're referring to. And by the way, Evolution also took this idea and also had their own policy.
Yeah, so have these things been accepted?
Wait,
have any of these things been accepted?
Yes, we have documents under isocpp.org. There's a standard document for library evolution policies and another one for evolution policies that actually been. Anyway, long story short, I don't want to hijack this, but I'm just going to say
that's
that
a big achievement.
Your ideas and notions are being acknowledged, but I also am not losing it.
All right, we have to wrap up here because we're out of time.
Yeah.
I put this quote on the slide
Thank you.
because, this will be hard. There's no easy. There's no way to change the world that's easy.